Hello and welcome to my video on using 16-bit bitmaps on the Nintendo DS. So I have a more complex scene planned and the demo shows moving around a larger scene. So what I'm going to go into is first off I'll go into how we set up the 16-bit color bitmaps. So as per the last video I did on 8-bit color bitmaps, we have modes for the main engine and modes for the sub engine. As you can see, there's 4 different backgrounds which can be used in each mode. The modes we are interested in are the rotation and the extended rotation, which are the ones we can use for 16-bit bitmaps. These obviously take up the most memory on the DS, so you have to be careful how much resources you're sort of using here. So as you can see, modes 1, 2, 3, 4 and 5 are primarily the modes we would be interested in using. So in a 16-bit bitmap, as for all the bitmaps, the pixels are arranged from the top left at 0, 0 to the bottom right, which is size dependent. They can be configured in regular mode, rotational or extended modes, which I won't be covering here. I'm only covering the regular 16-bit bitmaps. So the sizes are different as well, what we can use. We can't actually use 1024 due to size limits. The maximum size we can use is 512 by 512 due to the amount of memory which is used. So you can have up to 2 bitmaps maximum as per the modes here, and obviously that's due to the memory constraints of them. So one in 16-bit mode, the bitmaps obviously take twice as much memory as they did in 8-bit color mode. So a 256 by 256 pixel bitmap is now 128K, which is 1 VRAM bank. So if I go over to here, you'll see these are the video RAM banks which are available for us to plug into the mappable memory regions for the DS to be able to see and work with the video RAM. So one 256 by 256 image will be equal to 1 bank. So if you have 2 of those screens, that's 2 of those banks taken away instantly if they are 256 by 256. I won't be going over the setting up the locations or the sort of steps here, as I covered that in the 8-bit video. So as I said, the maximum size you can use is 512 by 512. However, if you were to create a 512 by 512 bitmap, then that would use all 4 banks, and that would only be able to be achieved on the main screen. So when it comes to the sub screen, these are the sort of main 4 banks, if you like, A to D. Only C can use, only the sub screen can use C. So it can only have one 256 by 256 16-bit color bitmap. And again, just like I said in the 8-bit video, the actual screen size of the DS is 256 by 192. So that means that some of that memory used, or rather allocated for the 16-bit bitmap, is not used. In the case of a 256 by 256 pixel screen on the DS in 16-bit mode, we have 32K, which is not in use, or rather is not visible, so you could allocate other things there. And then here I'm just sort of saying where in memory the main engine RAM begins and the sub-engine RAM begins. And then the advantage of working with the 16-bit bitmaps is we obviously do not have to worry about color palettes anymore, as we are working with raw 16-bit colors here. So as I've said numerous times, this is the format for a 16-bit color. We have 1-bit alpha, 5 bits blue, green and red. So by setting these bits, we can achieve the 32 different blue, green or red color states. And then, as I sort of said in the last video as well, is when you're actually reading and writing directly to VRAM, you can only access it in unsigned shorts or U16s. But as each pixel is that size anyway, there's no real sort of dilemma when in 16-bit mode. And this is how the screens are sort of laid out here, with 00 being at the top left, as I said, and then 256 by 256 being at the bottom of the bitmap, and then that's the actual byte size there, so that is equal to a 128K. So we'll go over some pros and cons of bitmap mode. So when we use bitmap modes, we can use a lot of memory, but we have more control of the shapes and sizes of the images we draw. When we use 16-bit mode, we literally can have any color which the DS can actually display. So, and there's obviously no color palettes to work with, and we by directly using splitting functions, which is transferring pixels from like an array or a map, if you like, to the visible screen, that gives us more control than what we would have with tiles, potentially even sprites as well, as we can kind of do away with them and just use the splitting functions to copy whatever parts we want. And without working with sprites, we get to use the 16-bit color range rather than be limited to either 16 colors or 256 colors from a color palette when working with sprites. This also makes working with like large levels kind of easier as well, as everything we draw to the screen all is working in the same sort of coordinate system, rather than parts of the level having to be drawn in steps of tile sizes of 8 by 8, or the limit with the width and the height that sprites can go to. Again, the cons is obviously when you're working with these 16-bit images, working with individual pixels obviously takes up a lot more memory than using tiles or 8-bit bitmaps for sprites. One thing we can do to kind of overcome some of the memory issues is we can use a compression to try and squeeze more image data into less memory. So one of the if I open up my image converter, which if you've been going through these videos, you should have come across that one already. So you'll see that these two tabs here for RLE bitmap mode. What that is that's run length encoding, which is a kind of compression format. So you can copy your images in here, and then if you export in this mode here, then it will compress the pixel data. I'll go over the sort of format, what that is, and how we can use it here. So the run length encoding methods, there's a few ways you can kind of do it, but basically what you're doing is you are sort of reading a sort of pixel color from the image, and then you're counting how many times in a row that color is used, and then instead of storing that color value, the amount of times in sequence that the color was drawn, you can instead use just two numbers to record like a whole line of colors. And then as long as you sort of stick to that, then potentially you can reduce the size footprint dramatically. Of course, if you have like a very noisy image which has lots of different colors in it, say like a star field or something like that, then that could potentially even create a larger image than if you didn't compress it. So you would kind of, when you play around with compression of like images, you kind of need to see whether you are actually making any gains with compression or not before using it in the final thing. So in the 8-bit compression format, everything is using unsigned bytes in the exported data for the tile or the image. So what that means is that the maximum sort of size you can use for those images is 255 by 255, as the array data is all in bytes. Whereas when you're working with 16-bit images, everything is in unsigned shorts. So the maximum size of that is 65536 for the width and height. So no limitations there size-wise. It's fairly straightforward. When I get into the demo, I'll show you the. In fact, I'll show you some of the graphics in the demo before we go ahead. So this picture here has been converted into 16-bit and also compressed, and that makes it slightly smaller than what it would have been. These are the tiles we'll be working with here. So we have like a sprite sheet of all of the actors here. These aren't characters I've created. These are from a game, I think it's RPG Maker or Game Maker, something like that. There's a sprite sheet I used and found from the on Spriter's resource. These are just some characters I thought would be more interesting. So you'll see that the we have an empty color here. This is basically a color which has an alpha value of 0. So if I open this up here, this is obviously like a magenta color here. At the bottom is the alpha value, which is how translucent or invisible it is. So you see there it's semi-transparent, and if we put that all the way to 0, an example will show you what I mean. So if we put that back to half and then fill this square here, you see we can still sort of see the like background beneath it. So if we copy that across and then paste it in, you'll see there that it's over the top, but because it's got an alpha value less than 255, it kind of blends with the image below it. So when creating like a virtual sprite sheet for working with 16-bit bitmaps, always make sure that the sort of sprite ones have an alpha value of 0 as the background, otherwise they will be rectangular when you kind of paste them to the screen. And then we have slowly whittled it down to this one here for the background tiles, where we have a number of sort of like floor layers, if you like, and then a bit of path, and then some other sort of obstacles to go around the sort of 2 houses here. So I think the houses are based on some Zelda graphics. Same with the trees here from the Super Nintendo. This tree here is kind of like a scaled up version of this, but it's kind of been converted into a vector graphic at the same time to kind of smooth it out. So you see there's a load of like blank space around here. And then what I also had as well is, as this is a larger sort of scene, we have 2 sort of like level maps. We have this one here for the floor. So each of these colors represents 1 tile in the level. So everything on the floor map you can walk over. And then if I bring this back up a minute, do a side by side here so you can kind of see what I'm talking about. So each of these pixel colors here actually represent a tile from our backdrop sheet, but this this map here is limited to only the floor tiles. So this this magenta color here is actually an invisible color, which is not used. And then the dark brown is obviously the first tile here, and then the 2 green colors are obviously these 2 green ones here. So the reason why I kind of use this method here is we can then convert this into a bitmap, an 8-bit bitmap, and then copy that array data into the code. And then there's also the other one here, which one is it? It's this one here. Nope, it's this one here. Obviously I worked with this a few times. So this map here, this contains the obstacles here. So this map served as two different things really. So not only does it show where the placements for these objects will be on the level, but I also used it to create a collision map as well. So not only will we have the positions for each of these objects, we will also have like a collision area for them. So one thing to note is the tile sizes here is a 32 pixels by 32 pixels. When it comes to objects which are obviously larger, like this large tree here, or the houses, this is the final one here, but you'll see that the this color here this is the large tree, so there's like a gap around it here. If I bring the grid up, so you disregard the top line. The top line of the image is not sort of exported. This is just like a color palette used to describe what's actually in the image. So as you can see, each of the large trees has a load of blank space around it. Basically, the one sort of color is always the top left tile, if you like. This here, these two cyan or aqua sort of colors, these are both of the houses here. And then you see there's like a significant gap around these. If I bring up the sort of work in progress image here, give you a better understanding how I sort of did that. So this was me sort of playing around with like a quick sort of level. So you'll see here the sort of like I created almost like sub tiles when plotting these out, so you can think of these as almost like a palette of objects here I kind of kept separate. So I knew that I could sort of copy and sort of paste these anywhere in here, and then they would have the sort of space around them free. So as we're not sort of working with tiles at all, the you can kind of make the sort of size of your levels now whatever you kind of want. I chose literally just to stick to 32 by 32 as it was a kind of manageable size, and also in this one here as well. So we have, not only in here do we have all of the level sort of tiles, these two colours at the end here represent the player start position on the level, which is there, and the white colour here represents a random NPC position, as you'll see when I run the demo in a moment. So I thought I would show you what's kind of in there and how it was designed. When the sort of the project which I will post up online, I will include both of these, the obstacle map and the level floor map, along with the sprite sheet and the backdrop sheet which I used as well, so you can play around with those. Like I said, some of these are slightly altered by me, they're not sort of original creations by me. So I'll sort of get back to some more of this here, just talk a bit more So when it comes to blitting images, what am I actually talking about here? Well, what I'm talking about is copying parts of these images. So when we export them into like one sprite sheet, if you like, when we export all of the graphics, it's going to be in a massive virtual sort of bitmap, if you like. It will be exactly like this, going across in pixels in like an array. So to be able to sort of copy and work with these, we need to know the sort of top left starting area of an individual tile. So the girl in this case here, she's 32 pixels by 32 pixels. If we wanted to copy that frame, we need to know where the top left of the graphic is in the sprite sheet. We then need to know the width and height of the rectangular frame we need to copy. And then what we would do is we would then systematically go from top left all the way to top right, and then go down a row and literally copy the whole sort of rectangle pixel colors to wherever the screen location we wanted to do it. So to blit, we need to know the source X and Y position in the sprite sheet we are copying from before we can kind of do the sort of blitting process. So the pros with blitting here, so when we carry out blitting pixels from one location to another, unlike when using sprites or tiles, there is no clipping process handled for us. Clipping is the process of stopping pixel data from being written to off-screen areas when an image goes outside the margins. So you can think of if we have like an off-screen bitmap, which we do as like just an array of U16s. If we wanted to copy this pixel data into this buffer, we need to make sure that every part of the image is fully inside it. So we would need her to be totally inside. If she's outside slightly, then obviously this location here would be outside of the off-screen bitmap array. So if we try and write data to it, we potentially would cause a crash in the system, or who knows what, you know, which obviously we wouldn't want. So what we would need to do is to only draw the physically visible sections from our image. So we would disregard anything which is not overlapping our off-screen buffer. Same here, we would only draw the top part of the image which fell within the region of our off-screen rectangle. When we're working with sprites, obviously we don't have to worry about that. It's all handled automatically by the DS. But when we are having to do all of the drawing manually, pixel by pixel, we obviously need to take care about all of that. So like I was saying, the pixels could leak into other areas of the computer's memory and cause system crashes or other undesirable effects. So to avoid this, we need to work out the viewable area of the image we're copying, as I said there. So when we are sort of drawing this image here, we also need to take into account the source, the sprite sheet's width and height. So when we are copying, we are sure that we are copying a legal, as in a viable part of that image. Otherwise we would just be sort of copying garbage from somewhere else in the memory to the screen. So what we'll be doing in the demo is we'll be creating like an off-screen array. We'll do all of our drawing to this off-screen buffer, and then when we're finished we will then copy that to the top screen. And that will make up our sort of scene, if you like. So because we're doing all of the plotting to an off-screen buffer here, creating the illusion of scrolling is a lot easier, as we're literally just, the way that we sort of do things is we move all of the tiles rather than the obviously the off-screen buffer isn't changing, but all of the tiles moving however we sort of place them creates the illusion of scrolling. So we can kind of create a lot larger scene this way. So I'll get into the code now. So I'll show the demo first. Fortunately, I can't sort of fit the screen in here. Let's see if I can rotate it around. No, that's not what I want. There we go. So here we go. This is the top screen here. This is the bottom screen here. So one of the things I've put in is our playable character, when we sort of start the level, is randomly chosen for us. So in this case here, we have the sheep character here. And then we have an NPC at the top here. So what the NPCs will all do is they'll randomly turn around every now and again. So I've had it so that you can kind of slightly overlap things to kind of give you the feel that you're kind of looking at it front on. So obviously the layouts of the sort of floor tiles are not that great. It kind of looks ugly and jarring, the way that they're kind of laid out, but this is just to give you like a demonstration of everything that I've done here. For your own projects, you would obviously create a load of different tiles where they give like a smoother blend in between different floor types. So we've got the houses down there. If I press return here or start, you'll see we've now changed into someone else, and then all of the NPCs also change as well. The one of the other things I've put in there as well is I created some separate collision areas for the different playable characters, as they're all slightly different in their sizes, as you would do in a real game. If you've got loads of different sized characters, you would obviously want to have collision rectangles which sort of hugged closely to them, so the collision looked fair. So I'll jump into the code now and go through some of the core bits and pieces that I want to talk about. So first off, we'll talk about the run length encoding. So if I bring up the background image, so as you can see with this image here, this color here, there's loads and loads of it. So this is kind of like a perfect example here. In fact, it changed there. So you see these numbers here match what's found here when this image is converted. So one thing to note is that the I didn't actually this is actually a 32-bit image here. The conversion only took place in the image converter. One of the things I do first off is I obviously convert all of the pixels from 32-bit into 16-bit color, and then create the sort of compression. So what we do to work with the run length encoding is first we take a color. So here's our first color, and then there's only 2 occurrences of that color before the color changes. In fact, it's probably better to show you on something else. Anyway, the way it kind of works is you have the pixel color, and then you have the count of that pixel color, and then you go on to the next pixel color. So we're not taking every pixel, we're only looking at the changes and then recording how many times that color was actually found, which is what's actually happening here. This isn't the although it kind of is a decent image to kind of show you, because all of the colors are nearly the same here. We didn't get a better kind of saving. For example, loads of these sort of like dark blue colors could probably all be replaced with a single one. So with a bit more work, I probably could have reduced the memory even more. So to draw the sort of compressed image, if I get into the routine for doing that here a minute. So some of the code from this video over the 8-bit one has changed slightly, as we obviously are working with U16s now, not U8s. Where are we? Here we go. So this is the code here just to draw a compressed full screen image. So we, as I said, this is the pointer to the image data. We take one unsigned short from it, store it in our color. We then take the next unsigned short, and that will be the draw count for that color. And then the this pointer here points to the off-screen buffer for the bottom screen, and then all it does is it just continually plots whatever color we find for the draw count, as you'll see here. draw count is subtracted from 1. And what we also have as well is we have a pixel counter here to make sure we don't overrun the size of one full screen. So if I bring this up here, you'll see that one full screen is 256 by 192. But obviously this is not in bytes. This is in U16s or unsigned shorts now. So that's the way that you, or rather the way that the code which I've created for the compression works. And this is just the method to uncompress it. It's pretty much exactly the same for the bytes, except you have U8s everywhere instead of U16s for the bytes. So some of the other things I've introduced in this demo, which is worthy of note, is the way that I was the way I've been handling loads of the drawing all of these like tiles. To handle working with loads of these, I created a thing called a scene object. So one of the interesting things about the DS is it kind of borders on the past with the sort of tile systems and tile maps, but also all future machines which use working with sprite sheets and textures. So as a result, I can kind of use the scene object structure which I would use when creating stuff on any sort of modern console or on the PC. The way that you kind of do things is you, in our case, when we work with these scene objects, what we need to know is we need to know the sheet ID, which is just referring to which array the graphic data for those images is stored, and then we need to know the parent image size. So for the if I bring this across here, this sprite sheet here, its size is 384 by 256. So you don't have to have these sprite sheets to be powers of 8 anymore. They can be whatever size you kind of want them to be now, as you're not restricted like you would be if you were working with tiles or sprites. But we need to know the image sheet size for the parent, so we can copy the pixels correctly. And then we need to know the source and destination rectangles. So the source rectangle is literally where our image is inside the sprite sheet, and then the destination rectangle will be the destination on the well, it can either be the destination on the screen, or it can be the world coordinates on the level. Everything I've kind of done in this demo actually works on world coordinates in the level, as these are converted by the we have like a virtual camera we work with here called the render camera. This is something that you do on all the modern machines as well. You kind of have like a camera which is the viewport into the level, and then you transform all of the objects to be drawn on the physical screen if they fit inside the render camera. And then you also have like a render camera bounds rectangle to stop the render camera from going outside a viewable area of the level. So a render camera bounds is literally like a rectangle around the actual level, which is obviously dependent on how big you sort of make it. And then this function here centers the render camera on wherever you kind of want to point it at. And then inside this function here, it checks after it's centered the camera on this point, then checks to see whether the camera is inside the camera bounds. If it's not, then it auto corrects the position. And then these functions here, just this one here sets up the render camera bounds, and this can be used to set a position independently of centering it. So most of the other stuff here, the ones I'm kind of interested to show you is how we sort of draw one of the scene objects. So to make things nice and simple, I created what's called a render list. All this is it's basically like a list or an array of scene objects. We give it a fixed size, so we don't need to dynamically allocate the size. And then we monitor how many are in this list. So one of the good things about using this is you can kind of draw a whole level to one of these lists. And as long as you don't need to change anything in that list, you can literally just keep it for the duration of that level being active. And then with one call in here, this will literally draw every item from that render list to our virtual screen. And this function here as you can see here, the in fact I didn't include this here. This is a key thing here. So this is sometimes useful as well. As we're not working with dynamically allocated memory with these render lists, we can literally just set the list count to 0 and then treat it as it being empty. So one reason why you might want to do that is if you had like a render list of collectible items, say, you might only want them to be added to that list if they were active or visible on the screen. And obviously that would change from update to update of the game. So you might want to empty that list after you've drawn it, ready to be worked with again. And then all this does here is this iterates over that list and then calls the draw scene object function above. Now what this one does is this one handles the clipping process using rectangle overlap functions here. We check to see whether the destination rectangle of our scene object overlaps with the render camera. If it doesn't, then no more action needed. If it does, then we transform the destination location by the camera's X and Y position. So what that does, by doing that, we physically make sure that those objects will then draw to the buffer, kind of faking the scroll process. And then the next thing we do is, if I come back to here, you'll see we have a uses transparency flag in here, which is important because we need two different drawing routines if it does and if it doesn't have transparency. So if you're drawing like one of the floor tiles, there's obviously no transparent areas there. So by checking for transparency, that obviously is a bit slower than not checking for transparency, which is why we separate the functions here. And then also another thing to note as well is these split scene object functions only have been set up for the top screen. Obviously you can adapt them to use the bottom screen if you wanted, but there are separate functions already in here. Initially I just created these same sort of functions from the 8-bit demo. These will draw to both screens. So the transsplit for the 16-bit one here, you'll see that it doesn't differentiate between the top and bottom screens. One of the things I did was, where are we here? In fact, it's going to be at the top here, is I've created like, we have our sort of virtual screen, if you like, which is basically an off-screen buffer for the screen. And then we have some different rectangles for checking where an image is going to be blitted. So the surface rectangle area, this refers to the whole size here, whereas the screen one only refers to the top screen for the main engine. As I didn't think for like a proper game that you would be wanting to use both sort of screens. So there's a various functions here. These are the main sort of ones, the Blitz 16 ones. They're kind of similar to the 8-bit ones, to be honest. So if you've followed the videos before and you've seen the previous one on the like 8-bit one, you'll see that loads of this stuff is pretty much the same, except now we are working with different sort of sizes. Obviously this one here wasn't in there. Play around with some of this to get a feel for what's happened. This is just drawing like a gradient to the part of the screen there. So for example, the pixel set, or rather pix set function, we can now work with 16-bit colors, and then everything here is kind of working with the 16-bit pixels now rather than the 8-bit ones. The only ones which are kind of a bit more in depth are the sort of built-in functions here, where we kind of split things up. If a whole image fits inside the sort of surface, then we can sort of draw everything fine. Otherwise we have to sort of calculate which parts are visible and then which parts to skip over. So I would definitely advise you to kind of look through all of this here to see what's kind of going on. But the whole sort of render list thing definitely changes everything. All of these are straightforward here. All we're kind of render list thing, all we have is a few sort of very few functions in there. So if I bring up the code for that one, all we're doing is copying the key data from the scene object pointer to one of the scene objects in the render list. And then there's also this function here which I use in some of my other sort of games here, which is useful, where you can kind of think of like a render list could actually be like a whole sort of layer in your game. So you could have one final render list, which is say a composition of a number of different render lists. So you could have one render list for a floor, one for like a mid viewable section, say, another for a foreground. Could even have one replacing tiles for fonts, and then maybe you just have one render list to draw everything. So you would then want to copy the other layers into the sort of main render list to draw everything in one go. So lots of the stuff is organized in the level manager. We have our two arrays. We have our floor array here and our obstacle array here. So once you have drawn out your levels, all you would do is open up the DS to tile converter, and then select 8-bit, and then put in the size of the level, and then you just drag it over like so, and then you would just save that out, and you do the same with the floor one as well, and then you're just going to copy those levels in then. So if I open up that one there, that's all it is. And that's all these are here. And then these things here, these just correspond to what these numbers are. Obviously you need to change some of these slightly. So another useful thing here is to make some notes in here for when you're doing the various things. So there's only like 3 images that we kind of use. We have the backdrop, which is this one here for the subscreen. No, sorry, the this image here. We have the actors, which is this one here, and then we have the background subscreen. So as they're just all arrays, there's nothing to set in video RAM for any of that. We literally just copy in the graphics for them all. As you can see, it's a massive array of pixels, basically. Like it's almost like a pix map, really. One of the key things that we kind of need to do is I have this other thing here, which is a rectangle list. So the reason we kind of set these up is to make working with these tiles easier. So if I open this back up again, so in the view here, you'll see I've got in the grid settings 32 by 32. So what this rectangle list will do is it will enable us to store the image frames located inside the parent image sheet. So for the sprite sheet one here, when we're working with these actually do use a dynamic memory allocation. We use the calloc function there to clear and allocate memory. So the sprite sheet here, we need to create it first, and then we add the various parts there. So if I sort of bring up the header file for that, put that there. Then you'll see the what we need is we pass in our newly created rectangle list, the start coordinates where the images will begin, the width and height of the sort of rectangles we are adding. We then need to say what our parent size image is, and then how many to add, and then whether the next x coordinate will start at 0 when it reaches the width of the sheet. So for example, if you put that to not start at 0, it's basically 0, 0 there is the top left where we're starting. If we didn't want the dog, then we would start it at 0, 32. And then you can see there's a 12 frames across, basically. Again, I made note of that in here. Each actor has 12 frames. So once you've created these rectangle lists, it makes working with sprites a lot easier. You just need to remember, or rather record, where everything starts. So we have an enumeration here to say where everything starts. So the dog starts as actor 0, the cat is actor 1, but to get to the rectangle for the cat, we literally multiply this number by the graphic actor animation frames number. All of it's fairly straightforward. By creating all of these frames for us, we don't have to remember all the time we wish to draw something, which rectangle to use. And it also makes using the scene object structure easier as well. So we're using mode 5 for both of the screens, and then we also are using a tile map for each of the screens as well, still, just to handle the text. So all of the sort of core code is in the title screen thing here. There's not a lot in here, it's all kind of straightforward. All you need to do each time is make sure that you draw one of the surfaces, the top or bottom at the end of the scene. So the level manager here, if I come back to that, you'll see we have the render list set up here. We have a floor one and a scene objects one. So the scene objects is literally just the background. We draw everything once and that's it. That's the beauty of the render lists. So you could put a huge, massive level in each of these, and then pretty much not really worry about it. Obviously, if you have a load of stuff that constantly animates, then you would probably have to have another sort of render list. The level manager function, where are we? Oh yeah, the draw backdrop function. So to draw those levels is as simple as that. You literally just pass the render list to scene2d, draw render list, and then it does everything. Obviously you need to make sure you draw things in the correct order, otherwise they'll be wiping each other out. So the setting up of this is very straightforward. In the level manager initialize function here, basically clear both of the render lists first. And then we also create a RectList as well for our level obstacles. Because we have the when we set up the rectangle lists for the backdrop objects, in here we obviously have how big everything is, so we can reuse these again to take the actual sizes of those objects and add them to our level obstacle list when we encounter one when we create the level. So we kind of create the level in two parts. We first iterate over the floor map for our level. We obviously need to know what the size of the backdrop image is. And then this function here, create new scene object. You'll see we have like a rectangle for our source frame. Where we work with the, we get the rectangle for the tile from the backdrop list. So if I come back to here a minute, this iterates why we sort of do all this first. So we go through setting up the the object parts, or rather the image parts for the backdrop, which is all of the floor or the trees and houses. These are just referencing how many parts to kind of take. And then the reason why we get the tile from the floor map here. So the first one is 1, but obviously we need to subtract 1 from it, because if I bring up the floor map, you'll see that the first tile was obviously an empty tile, which we need to just allow us to kind of show what the color palette is at the top for our tiles. So we get which tile we need to use, and then we use the RectList for the backdrops to get the rectangle location where that tile's source is. We then create a new scene object with our backdrop image ID, our source frame we pass in. We then pass in the parent size, and then the position is a vector 2, which is basically just an X and Y integer there. And then that's all you need to create a new oh yeah, and then you also say whether you want the or rather whether the source image uses transparency or not, and then you just add it to the scene. So you'll notice here that the position X and Y is going up in tile sizes. So we're literally, everything you add to these render lists are all in world coordinates, and you can forget about it. So that just creates our floors. And then the next one, there's a bit more in there. It kind of does exactly the same again, except it's using the obstacle map this time, which has the trees, the player and everything. Now this one we have 2 things in, as we can create the collision objects at the same time that we create the images for the render list. So we connect our data to the relevant level map, and then again we reset X and Y for our positions for these objects to go up in steps of 32. If a tile is greater than 0, then we will draw it. Now one thing to note is we subtract 2 from it this time. So the reason for this is we need to skip over the other back blocks in here. So if I bring this up again here, which one is it? So as we've added all the rectangles in here, you see we have to get to the tree, or rather the fence, which is the first tile. We obviously need to skip over all of these here, because obviously we're only interested in the frames from the fence onwards, which is why in here, where is it? Yeah, there you go. The fence starts at tile 10. So we added the first 4. If I come back to here, lots of jumping around, sorry about that. So you see we add the first 4 frames here, which is the floor. Then we add 5, which is the path. So we need to skip over 9 tiles basically. And then at tile 10, that will be where the fence starts, which it does there. And then you'll see the stuff in the data map here. We need to translate these numbers again as well, so that they get to the right one. So we get our source frame from the backdrop list, and then this new one here, hit block, we can take the source frame width and its height. So to create the illusion that we can kind of overlap the objects to give it that sort of a top down but slightly forward look, we subtract 15 from the source frame height. Then we create a new scene object as before, and then we add our hit block to our RectList for our level collision objects. If the tile we get obviously is less than the player tile, so you see these tiles here kind of represent everything after the fence. So if our tile is less than the player, then we know it's going to be like a wall object that we collide with. Otherwise it's an NPC or the player, and then we call the add start position. And obviously we adjust the X and Y position. So this is exactly the same as these defines here. So these level block sizes, these are basically like the size of the tiles you're working with. So everything here is 32 by 32, but if you had something larger or smaller, then you would obviously change the block sizes here. The level map width and height is obviously the maximum size of a level. So if you had a level larger than 32 or taller than 32, then obviously change these as well. And then the sort of collision is fairly straightforward. If you want to check for a collision with anything, pass in the source collision rectangle with your object, and then we just iterate over our level obstacle list and see whether it hits anything in there. Which is this is fairly straightforward. I'll quickly go over some of the player stuff, just so it kind of makes sense. So let's bring up our actor sheet. So you see here we've set up some animation frames here inside. As all of the directions have the same number of frames per animation, as I would advise you to do, we can literally use this here. So you see one, if we cover the dog here, for him walking facing upwards, you see frame 1, he stood still, then you would go to like frame 0, then back to frame 1, then to frame 2, and then you would literally just loop that animation over and over again. And then this is regardless of which direction he's facing. Everything is laid out in such a fashion to take all of that into account. And obviously this is exactly the same for all of the characters here. The only other thing you need to bear in mind is how many frames you need to skip depending on what direction they're facing. So when they're facing up, we obviously don't need to skip over any frames. When they're facing right, we skip over 3 frames to get to the right ones here. 6 is down and 9 is left. So these just give us some extra sort of quick helper arrays here. To start our position for the player, we literally just look over the start position list until we find our player in there, and then we set their horizontal and vertical position here. So for our player here, you'll see we have a scene object, we have a tile base. What that is referring to is basically, depending on the type of actor, that refers to our starting tile. So that would be 0 there, that would be 12, 24, and so on. Again, that just refers to actor animation frames. What you kind of want to do is trying to create defines for all the parameters in your game, so that changing things is as simple as just tweaking a few numbers if you decide to change the graphics. And then just goes through after we've set their position there. Got an error check we're doing. We set up an animation timer. We have some states. And then this just creates like our tile is or rather our type is which actor here. And then, as I was doing before with the other stuff, we literally just create our frame from the sprite list. So we have the we add the tile base with the tile facing here, and then we have facing down as the start for our player, which will always be one of these. And then this is just the move function here. And then the key thing here is centering the render camera on our player. And then it's as simple as that. Once you have all of these things in place, it makes working with everything kind of simplistic to some degree. The NPC manager is kind of duplicates the player stuff to some degree. Isn't really anything worth going over in here. It's pretty much exactly the same. The only real difference is we have like a kind of different structure for the NPC. So I'll leave the rest for you to look at your leisure. I don't think there's anything else new which is really worthy of going into any more depth. Let me know what you think in the comments below, and I think that'll do it for this video. In the next one I will go over creating sound effects and some music, and we will go back to using sprites for the side shooter. Any questions or anything, just let me know in the comments below, and hopefully that's been of use to you, and I'll catch you in the next video.